All right, great. Recording is started. So good morning, everybody. Welcome back to another thrilling Math 115 lecture. Hand has been raised. Morgan, did you have a question? That popped up so huge on my screen. Okay, just an accidental hand raise. No worries. Wow, that really got my attention. Okay, well, if you need my attention, please do raise your hand because that worked really well. All right, looking a little bit lighter today on the attendance. That's fine, as long as these people are watching the videos. So, I have to share my screen. Share screen, start podcast. Okay, so there's an exam coming up on Monday, March 8th. Okay, I've been mentioning that for a while now. Review session tomorrow, or I guess tomorrow will be a review day, like our regular lecture will be a review. So with respect to that, please bring questions. Please come equipped with questions. So what we'll do is we'll start the review day, and then we'll have our entire 75-minute lecture. You guys can ask me anything that you want about anything that we've covered so far in the class. Okay. So if you want to come and say, I'm confused about XYZ topic, can you please expand on that? I can work with that. Or if you say, I have this specific problem from the homework that I could never get right, can you go through it? I'll do that. Or if you find a problem on the practice exam that you're like, this was really hard and I didn't understand your explanation on the YouTube video, then that will also work. Speaking of the YouTube video and the practice exam, I'll have the practice exam up shortly. It'll be up today. And the video solution will also be up with video solution. If I have to stay up until 3 a.m. and do that, I'll do it. No, just kidding. It's not going to take me that long. So that's about the practice exam and the review day. Really, just please do come with some questions because it's way easier if we do that. I'll bring a practice exam or two from some other classes that we can go through in case nobody has questions, but it's really your time, and the best way that you could possibly use it would be to really take advantage of it and make it your own. Because I sort of have to guess at what you guys are maybe not understanding as well as other topics. One message to the YouTubers. Please keep up with the lectures. Okay, I am noticing some students are not really keeping up with the exit slips. You know, that's 7% of your grade, which is just basically free. And some students are missing a lot of exit slips, and it's starting to be a little bit concerning. And I just don't want something bad to happen to the students who are attending class in this kind of asynchronous way because they get way behind on the lectures and then they realize late into the semester that like, oh crap, I'm really, really behind, and there's no real chance for them to get caught up. So to the YouTubers, please do keep up with the lectures. Please keep up with the homeworks and the exit slips. You know, and I'm speaking really from experience because when I was an undergrad, My very first online class that I ever took was an online psychology class. And I was like a math student, so I was like, psychology is whatever, and not really that interesting to me. And I kind of blew the class off. And I think like the entire second half of the semester, I didn't watch a single lecture until the day before the final exam. And I wound up getting like a C plus in the class because of that. And I was like kicking myself. I'm still kicking myself to this day. So don't be like me, okay? That's my lecture for the YouTubers. Okay, so any questions about anything administrative before we start in on the material? All right, if not, then we'll start. So I'm going to pretty much pick up where we left off last time, so let me remind you of where that was. Last time, we finished up a little bit of exponential equation stuff, and then we did pretty much everything on the logarithmic equations. And after we learned how to use or kind of navigate these logarithmic equations, then we moved on to, oh yeah, we had a quick review of all of these log rules, which I said were basically the main way to understand how to use logs. And you know, having like a really intuitive understanding of these rules probably would require you to spend some time looking at the proofs. I proved this number 3 here. Number 4 and number 5 are basically an application of number 3. This number 6 is just a definition. And then these ones are also follow directly from the definition. Okay, so if you look at the proofs of some of these rules, you might get a better intuitive understanding. But the main thing that you need to know is how to use these rules to manipulate equations involving logs. Okay, so if you have an equation involving logs, I'd encourage you to come back to this page and look at these rules and see, are there any of these rules that I can use to kind of rearrange this equation? And probably with enough trial and error and just rearranging according to these rules, you'll probably get where you want to be. Okay, so look for the rule which looks like it could apply to your situation, and then, yeah, give it a shot. Okay, and then we kind of moved on and talked about some examples. Actually, we just talked about one example. And that's what we're going to continue doing today, is just a bunch of examples of like word problems and log equations and that sort of thing. Because I feel like these word problems for the log stuff and the exponential stuff is really kind of one of the hardest parts of this chapter, I guess. So I want to spend some time going through a lot of examples because I know students have been asking for more examples on the exit slips. So that's what we're going to do. Okay, so this first one, we were supposed to do the following. We wanted to find the time required for an investment of $10,000 to grow to $18,000 at 2 different interest rates. So the first interest rate was compounded 6% annually, and then the second interest rate was compounded at an annual rate of 6% compounded continuously. Okay, so we just reminded ourselves of what do the corresponding equations look like, okay? And these are really, you know, not yet specific, okay? This is just the general form of an equation describing how money grows according to continuous interest. Okay, so what we had to do then was sort of take each of these kind of vague formulas and make them fit our specific example by taking information which was in this big paragraph here and using it to find out what was the value of a naught, what was the value of r, what was the value of a of t, and what was the value of t. Okay, so we have like 4 unknowns in this equation, and from the paragraph we learned 3 of them, and the question was asking us what is the 4th one. Okay, that's basically what was going on here. Let me clean this up a little bit. So we noticed from the word problem we say, okay, it grows to $18,000. So that's my ending balance. So that's why I put $18,000 on the left-hand side here. And then my initial investment was $10,000, which is why I put $10,000 where I had a naught in my general equation. Okay, and then I knew that interest rate was being compounded 6% annually, so I knew that r should be 0.06, so I put it in here. I did 1 plus 0.06 is 1.06. And then I just needed to find out what t was. That was all I had to do after that. So I kind of divided both sides by 10,000, and I was left with an equation that looks like 1.8 equals 1.06 to the power t, at which point I applied the natural logarithm. Now, why did I apply the natural logarithm? I applied the logarithm because if I want to solve this equation for the exponent, I need to get the exponent out of the exponent, basically. I have to get the t here down on just like the regular level, okay? So I have to get it out of the exponent, and the way I do that is with logs. That was the reason logs were invented. Okay, so I put everything in the log, and then I recognize that when I do ln of 1.06 to the power t, I can use the power rule to rewrite that side as t times ln of 1.06. And then I just have an equation which looks like a number is equal to t times some other number, so I just divide those two numbers to get t. And if you plug those numbers into your calculator, you get something close to 10 years. So that was how we did that one. And then the second one here, I erased it because I felt like I had to rush, and I want to go back over it. So the second one is using continuous interest. So the formula we're using here is a of t should be equal to a naught times e to the kt, where k is our interest rate. Okay. So I had the following equation. My a of t is still the same. It's 18,000. That's my ending balance. My starting balance is still the same, still 10,000. Then I have e, that's just a number. And then k is going to be my interest rate. So I put 0.06 here, and then t. And now again, my goal is to take this equation. It just has one unknown, and the unknown is in the exponent here. So the very first thing I'm going to do is divide both sides by 10,000 just to make the computation easier. I get 1.8 equals e to the 0.06t. And that was kind of useful to do because now when I apply ln on the right-hand side, I don't have to worry about this pesky 10,000 being here. I got rid of it. When I do ln of both sides, I again have ln of 1.8 on this side. And then on the other side, I have ln of e to the 0.06t, which is the easiest thing ever to evaluate. The only thing we do is just, get rid of the ln and the e. It just becomes 0.06t. And that's equal to ln of 1.8. And so t is going to be equal to ln of 1.8 divided by 0.06. And I can just plug that into a calculator. So I'm going to show you how I do that. I would just use a calculator, and I would type on my calculator ln of 1.8. And then I would take that number and I would divide it by 0.06. And then I click equals. And what do we get? 9.79 something, or 9.80 something. So this is about 9.80. So what did we learn? From this entire problem, we learned that all interest rates are, or all, not interest rates, but all ways of compounding interest are not created equal. Okay, when we earned 6% compounded annually, it took us 10.09 years for our investment to double, or no, to grow to $18,000 from 10,000. So we 1.8'd our investment, and it took us 10.09 years, so a little over 10 years. When we used continuous interest at the exact same interest rate, okay, the exact same rate, we wound up growing to $18,000 in a little less than 10 years. Okay, so if you're the one who is investing, then maybe this continuous interest rate is actually better for you, okay, because you get more money faster. And if you're borrowing money, then maybe you would rather have an interest rate compounded annually, because then your interest, i.e. the money, the extra money that you have to pay back, grows more slowly. Okay, so that's this example using different types of interest. Let me pause before I move on to the next one. Ask, do we have any questions on this interest stuff? Or about compound interest or simple interest or anything of that nature? Okay, no questions. By the way, there's a special word they use for this tomfoolery. They call this 6%. They call it the, quote, nominal rate. And by nominal, they mean in name only. In name only. Okay, so if you see they tell you that there's a nominal rate of 6% compounded ... Okay, it could be compounded in a buttload of different ways. It could be compounded annually. If it's a nominal rate of 6% compounded annually, then it means what you think it means. So annually is the usual. But if they give you a 6% nominal rate compounded semi-annually or monthly or continuously or daily or whatever, then the actual interest rate that you're going to be earning is going to sort of vary somewhat in either direction. So the banks will try to use this to hurt you, and I don't want any of my students to get hurt by a bank. So just be aware of that lingo that they throw around, because if they tell you that you're going to earn a nominal rate of 6%, you might actually be earning a little bit less than that. Or if they tell you that your interest rate on your loan is only 6% nominal, it could actually be a little bit worse than you think. Okay, so just be aware of that. That's free life advice from Tom. Okay, so next up we'll do this problem. Okay, it's just another word problem, so let's read it together. It says that the light intensity L in lumens at a depth of X feet in Lake Elizabeth is given by this kind of nasty looking equation. It says that if we take the log of the number of lumens divided by 25, that'll be equal to negative 0.025 times the depth measured in feet. Okay? So as the depth gets larger, we expect this right-hand side to become more and more negative. Okay, which means on the log scale, as the depth gets larger, what's happening? The depth getting larger means we're moving down on the log scale, which means that we should expect this number to be getting close to the value which produces more and more negative numbers. So this should be getting closer to 0 as this increases to negative infinity. Okay, so that's kind of how this equation works. And that makes sense because we should imagine that as the depth gets very deep, then the amount of light is going to be really small. Okay, so that makes sense. So I always kind of like doing that when I have one of these word problems. I just take a minute to take a look at that equation and try to understand what's really going on with this thing and play around with, okay, what happens as x is getting very deep, and try to have an understanding of like how to match that to, the problem here. So, if you've ever seen like Finding Nemo, right, when they go really deep into like Mariana's Trench, or the Mariana Trench, it's like super dark, and they meet that one like crazy looking fish with the lamp on its head. Okay, so we want to find the light intensity at a depth of 40 feet, and then we want to find out at what depth is the light intensity going to be 4 lumens. Okay, so the first one, let's just deal with A first. Well, we're going to try to find out what is the light intensity. So we have L equals question mark, that's what we want, and the depth is 40 feet, so x equals 40. So all we're supposed to do here is kind of take this information from the word problem, write down what it really means in terms of our equation, and then plug all that information into our equation and solve for the thing that we were interested in. So I'm going to need a calculator for this problem. I don't even have base 10 log on my freaking calculator. All right, I'll use Wolfram Alpha. Okay, so negative 0.025 times 40. Oh, great, that just gives us negative 1. So we get log of L over 25 equals negative 1. Now let me ask the class. And this is the step where I usually ask the class, what do I need to do here? So how do I proceed? How do I get L? Sure, we could split it up like that. Let's try it. Log L minus log 25. That's true. We can split it up like that, no problem. Now how should I proceed? If we want to take this method, this might work out, I don't know. Any other students want to take it from here or go back and do something else? I think both will probably work in the end. Take the log 25 to the other side. Sure, we can do that. We get log L equals -1 plus log 25. And now we're still faced with basically the same problem, because what was the problem here? The problem originally was that L is trapped inside of a logarithm. And here we run into the same problem. L is trapped inside a logarithm. How do we get it out? Yeah, we can use an exponent. Which exponent should I use? Kumar's really putting the team on his back right now. Can anybody like join in and help him out a little bit? Should we use E? We do E to the log L? What do we think? Does the class agree or disagree? Yeah, I think Aeon's got it. We should use base 10. Why should we use base 10 and not base E? That's right. Very good, Aeon. The log, when we don't write anything here, but we write log, okay, the implicit assumption is that this is a log 10. And the way we undo a log 10 is not by using the function e to the x, but rather by using the function 10 to the x. And that would be equal to 10 to the -1 plus log 25. Okay, so now on this left-hand side, log 10 and 10 undo one another, and we are left with just L. And that's going to be equal to 10 to the -1 plus log 25. So not the most elegant way to express our solution. We could plug this into a calculator and we would get something. I think probably the best way that we could simplify this would be to write this as 10 to the -1 times 10 to the log 25. Right, that was just a rule. I went from x to the a plus b is equal to x to the a times x to the b. So that's what happened in this direction. And then what is that? That's like 1/10 times 25 equals 2.5. Okay, so that's one way I could do it. I think there's a slightly faster way to do it, which I'll demonstrate now. So this was way number 1, and it works. Okay. Now I'll show you maybe a slightly faster way. Would just be to start with this step here where we just take everything to the power 10. On the left-hand side, I have a single logarithm, okay? And it's isolated and it's written all as a single log. I can just proceed immediately to, I think, what we called step 2 of the logarithm solving process. Okay, so the first one was, sorry, isolate the log and write as a single log if possible. And then the second step was use exponentials to undo logs, unless there's some kind of funny business going on. So since we've already got a log isolated here, let's just start with step 2. And I'll immediately take 10 to the log 10 of L over 25 equals 10 to the negative 1. And then what do I get? I get L over 25 is equal to 1/10. And then I get L is equal to 2.5. And that goes a little bit quicker. Okay, so usually with problems like this, we're often given something which starts out looking like this, and then we have to use the log rules to write it as a single log. And then we go here. Okay, that's kind of the usual process. So this problem could probably confuse a lot of students by sort of giving you the step which is in the middle, and then you think, okay, well, the first step is I'm supposed to use those log rules, so maybe I should go this direction. But it's sort of going a little bit backwards. It's not going backwards, it's more like going sideways, but it's not really moving you in the direction of where we want to go in the most efficient way possible. But you can do it that way, and if you like having the log L by itself, that's fine, but then it does require a little bit of thought to then simplify this final expression, or else I guess just plug it into a calculator would be fine too. But the problem can be done in a slightly more elegant way. Okay, got it. So yeah, one important thing that I want to go back and mention is thanks to Aeon, we noticed, okay, that log of L over 25, what we're really talking about is log base 10 if the number is unspecified. Okay, we called that the quote common log. The other one we had was ln of x is log base e of x. We call this one the natural log. Okay, but we don't want to get confused between ln of x and log of x. Okay, there are some textbooks, and it's possible that some of you have had another class. There are some classes and some textbooks where log is used interchangeably with ln, but that's not a feature of this textbook or this class. In this class, when we write log, we mean log base 10 if the number is unspecified, and if we want to talk about log base e, we talk about ln. So that's just to clarify if you guys have had any other confusion coming from previous classes or stuff like that. Okay, so that's how we solve A. Now let's move on to B. So B says, at what depth is the light intensity 4 lumens? So in this case, we're given L is equal to 4, and we want to know X is equal to question mark. Well, all we have to do at this point is set up our equation. We've got log of L over 25 is 4 over 25. And that's supposed to be equal to negative 0.025x. So we want to solve this equation for x. Okay. So here's what I could do. I could log a of x is ln of x over log of ln of a. I could use the change of base formula here. So I know that log 10 of 4 over 25 is going to be equal to ln of something divided by ln of something else. So my question to you guys is, what goes in this numerator box here? How can I rewrite log base 10 of 4 over 25 as 2 natural logs? What should go in my green blank? Okay, Abdul Rahman's got 4 over 25. Does everyone agree or disagree with 4 over 25? Let me use yellow. What do we think? The change of base formula said, oh yeah, sure, we can. On 4 over 25. Oh, okay, not quite. Let's recall what the change of base formula said. It said that the log a of x is going to be equal to ln of x divided by ln of a. Okay, let's go back and find that. See where that was. There it is. We learned that in week 7. Okay, so this is just a way of computing logs with a base that's not on our calculator. Okay, so maybe our calculator only has ln. My calculator here only has ln. So if I wanted to compute this, log 10 of 4 over 25, I would need to use the change of base formula. And what should go in this green box should be whatever is in my original log. And what goes in this blue box here, hopefully no one's blue-green colorblind, but if you are, let me know, should be this base here, 10. Okay. And now I can just compute those using a calculator. And I wind up with an equation which looks like negative 0.025x. And on the other side, I've got what was it? ln of 4 over 25. And then I'm supposed to divide that by ln of 10. Okay, and I get negative 0.8-ish. So I just divide both sides by negative 0.025, and I get x is equal to negative 8 divided by negative 0.025, which is equal to 32. And this should have been an approximately equal to sign. Okay, so that's how we do that one. So really, it was just about recognizing that this equation up here, log of 4 over 25 equals negative 0.025x, looks like some number is equal to some number times x. And what we do to solve those equations is just divide both sides by the coefficient on x, and we get what we want. There was just a little bit of trouble in actually finding out what is the number on the left-hand side. and we found out what that number was as a decimal using the change of base formula. Okay, so we can use that to compute logs of any variety that are not our typical natural log. And that's why many calculators only have a natural log button, is because you can use this change of base formula to compute any log by just using that one log. And that log is the most important, so that's the one they put on the calculator. Okay. Any questions about part B? All right, again, this is really just manipulating log equations and exponentials and that sort of thing. Okay, but there's a lot of ways in which this can kind of turn up in these word problems, so that's why I'm trying to go through as many examples as I can. All right, so we'll start number 3. I don't think we'll have time to finish number 3, but we'll start it. It's a hard one. And originally this was a problem about Facebook users. I thought I would rearrange it so that it's more modern friendly. Okay, so in 2016, this is not accurate information, by the way, but just imagine that in 2016 there were 1 million TikTok users. Okay, and then in 2024 there are going to be 845 million TikTok users. Okay, and we're supposed to use the following model, which looks like this kind of nasty equation. Okay, and the right-hand side, if we plug in A, K, and T, is going to give us the number of users in the teeth year since 2016. Okay, so if T equals 2, then it's f of 2 equals number of users in 2018. Okay, that's how this equation works. Okay, and it's involving this crazy looking function here. And so let's read out what we're supposed to do. Okay, and f of t is gonna express the number of users in millions. Okay, so in millions. Okay, so the first step we're supposed to do is figure out what A and K are. And then we're supposed to estimate the number of users in 2030. And then we're supposed to estimate the year in which TikTok reaches 2 billion users. Okay, so that's where we're going. So the first step is to try to package the information that's in the word problem in terms of our equation. Okay, that's always the first step. So the first thing they tell us is that in 2016 there were 1 million Facebook users, and then in 2024 there were 845 million users. So let's try to plug in and see what we get. We have f of t, that's the number of million users, and let's do the 2016 one. So in 2016, t is going to be equal to 0, and f of t, the million users in that year, is going to be equal to 1. And we don't know what A and K are yet, but let's go ahead and package this information in terms of our equation. We get 1 on one side, and the other side we're going to have 20,000 on top, divided by 20 plus AE to the negative K times 0. And that's equal to 20,000 divided by 20 plus a e to the power 0. And then we recognize, what is e to the power 0? Someone tell me in the chat, what is e to the power 0? That's right. Just like everything else, e to the power 0 is 1. So this looks like 20,000 over 20 plus a. Okay? And it looks like this is an equation involving one unknown, ultimately. We have 1 is equal to 20,000 over 20 plus a. So we can figure out what a is from this equation. So all we would do is multiply 20 plus a onto the other side. It's equal to 20,000. So we get that a is going to be equal to 20,000 minus 20, which is equal to 19,980. Plus a e to the negative kt, yeah. So we already figured out what a is. That's great. And guess what? They also tell us another piece of information. They tell us how many users there are in 2024. Okay, there are 845 million users in 2024. And we're going to use that information to figure out what k is. We already know what a is, so we can revise our formula now. Revised formula. We have f of t is equal to 20,000 divided by 20 plus 19,980 e to the negative kt. And now we just plug in. In 2024, what's t going to be? Well, t is going to be equal to the years since 2016. So we do 2024 minus 2016 is equal to 8. Okay, and then f of t is 845 million users, but f of t is expressed in million users, so it's 845. And now we package this information again in terms of this formula. And we wind up with 845 is equal to 20,000 divided by 20 plus 19,980 e to the negative k times 8. Or why don't we just call that negative 8k? Okay. And now we're going to try to solve this for k and kind of proceed with the rest of the problem. But that's going to have to wait for next time. So we'll stop here. Almost made it through this hard problem, but it's probably going to take me another page or two to solve the rest of it. So let's adjourn for today. Review session tomorrow. Please come with questions. Please come with concerns and ideas of what you want to talk about. I'll bring some stuff to work on in case nobody has anything, but I'm really hoping to have some engagement from the class in terms of that. I also have office hours starting now, going until 11:30. So 2 hours of free help. I'll help you with your homework. I will help you with your studying. I will help you with anything that I can help you with. So yeah, have a great day, everybody. Otherwise, stick around for office hours.
Professor?
Yeah, what's up?
Yeah, so on the last week's exit slip on Wednesday
Mm-hmm.
for week 7, so I filled yesterday's information in that by mistake.
I see. Let me look at the blackboard real quick.
Yes.
So this was, you put yesterday's,
Yes.
I see. You put the Tuesday, March 2nd information in the Wednesday, February 24th spot.
Yes.
Okay, did you do the exit slip for Wednesday the 24th?
Mm, no. No.
Okay.
I will do it today. Yeah.
Okay, then just put the exit slip for Wednesday the 24th on the spot for Tuesday the 2nd,
Okay. Okay.
like switching them around, and
Yeah.
just
Yeah.
put a note in there that says that, okay?
Oh, yeah. Fine.
Cool.
Okay.
Okay.
Thank you.
Yeah, no problem.
Yeah.
Looks like we got some other people in here. Is anybody sticking around for office hours and have some questions? Or Omkamar, if you have questions too.
I have some, but like my next lecture is after like 15 or 20 minutes.
Okay. Well, you wanna go through anything before that, or you wanna call it?
I think let me check first. So yes, I want to like understand the concept of holes again in a brief way.
Sure, holes?
Yes, yes.
Okay, yeah, no problem. Maybe I should put this somewhere else. Here, I'll make a new note. Go back to the black. Okay, so holes for rational functions.
Yes.
So we have f of x being a function, which is n of x divided by d of x, where each of these are polynomials. Okay, so the top looks like some polynomial like, I don't know, 3x squared plus 27x plus 1, and the bottom looks like another polynomial of some other form.
Mm.
Okay, and typically what we do is try to factor the top and bottom completely. And we wind up with an expression which looks something like this. We get like f of x is equal to like x minus a1 to the m1 times like x minus a2 to the power m2 dot dot dot, right? Where basically each of these are the factors of n, and some of them may be double roots or triple roots or so on and so forth. And the bottom looks something else. It looks like x minus b1 to the n1 times x minus b2 to the power n2 dot dot dot, and so on and so forth. For example, we might have f of x equals x minus 3 times x minus 4 squared times x minus 1. And in the denominator, we might have x plus 2 times x minus 3. Okay, so here we have a rational function. And we will have a hole in the graph of f of x for any x values which cause n of x equals d of x equals 0. So the numerator and the denominator are both equal to 0. Yeah, sure, Abdul Rahman, I can get to that in a minute. So let's check here for our example. For our example, we've got f of x equals x minus 3 times x minus 4 squared times x minus 1, and the denominator is x plus 2 times x minus 3. And my question to you is, are there any x values which will cause the numerator and the denominator to be equal to 0?
3, x equal to 3.
Yeah, we recognize here that we've got x equals 3 here could be canceled from the numerator and the denominator. So in our case, x equals 3 causes n of 3 equals d of 3 equals 0. And that tells us the graph of f of x has a hole at x equals 3. Okay, and so far we've really just we're kind of speaking a little bit vaguely about the graph. So what we've said so far is that there will be a hole there. What I haven't really said is what the graph is going to look like nearby, right? And that is not really something that we've discussed for something which is quite so complicated as this. But let's say we had something else that was more like, say we had x minus 3 times x minus 1 over x minus 3. If we had something like this, we could even draw the graph. Okay, because here's what it would look like. If we canceled those two, we would have that this is equal to just x minus 1, except when x is equal to 3. And in that case, f of x is undefined. So what does the graph of something like this look like? Well, it just looks like the line x minus 1. So we go down 1, that's our y-intercept. And then we would draw a line through it. Okay, my line goes through like that. And when x is equal to 3,
Professor?
1, 2, 3, yeah?
I'm just confused why the graph is like this.
Sure, so here's how this works. We have a rational expression here, right? F of x is equal to x minus 3 times x minus 1 divided by x minus 3. And in a perfect world where maybe we don't need to worry so much about holes, what we would do with these two terms here, x minus 3 and x minus 3, is we just cancel them out, right? It's a factor on the top and the bottom, right? Like, for example, if I have 2x over 2, that's equal to x, right?
Yeah, got it.
So this is just like a number. So we just treat x minus 3 just like a number. We have two things being multiplied in the numerator, which means that we can cancel out those factors.
Okay.
We're left with something which looks like f of x equals x minus 1.
Yes.
The equation y equals x minus 1 is a line. But we need to be a little bit careful because we originally started with a rational function, and we're trying to graph the graph of a rational function. Okay, And f of x is equal to x minus 1 is true as long as x minus 3 is not 0, right? If x minus 3 is 0, then we get like 0 times x minus 1 divided by 0 makes no sense. See what I mean? So in this case, we have to say the function's not defined, which is why the graph of our function looks just like x minus 1, except for that one little hiccup at x equals positive 3, then the function's not actually defined. Okay, so for example, what I mean is like, let's set f of x equals as above, x minus 3 over x minus 3 times x minus 1. And let's set g of x equals x minus 1. And my point to you is that these two things are equal as long as x is not equal to 3. So let's try x is equal to 0. We would get negative 3 times negative 1 divided by negative 1. And for g, what would we get? We'd get 0 minus 1 is negative 1. Oops, that should have been a negative 1, or 3. If we have negative 3 times negative 1 divided by negative 3, we cancel these, and we just get negative 1, and that's equal to g of 0 as well. Or if we try x equals 1, right, we're going to get the same thing. We'll get negative 2 times 0 over negative 2 is equal to 0. If we do g instead, we would get 1 minus 1 equals 0. So these things are the same. The only time when they're not the same is if we try to plug in 3. In which case, we would get 0 times 2 divided by 0 for f, and then g of 3 would just be equal to 3 minus 1 is equal to 2. And the issue is that when we plug in 3 for f, what do we get? 0 over 0. And on the right-hand side, we get 2. And my point to you is that not only can we not set these two things equal to one another, this thing doesn't even make sense as like a mathematical expression.
Yes.
Okay, so this is why we have the graph of this thing looks just like the graph of x minus 1 everywhere except for where the graph is not even defined. Make sense?
Yes, I got it.
So that's how holes work.
Yes.
Okay, that is how holes work. So basically, if you factor the numerator and the denominator, and you have a common factor, okay, then the x value which causes that common factor to be 0 is going to give us a hole.
Yes.
Okay. Lingering questions about the hole stuff?
No, I got it completely.
Okay, cool. Yeah. Then I'm going to go on and talk over these interest formulas.
Yes, so thank you, Professor. I'm leaving now because I have class.
Okay, no problem.
Yeah.
Have a good day.
Yeah, you too, sir.
All right, Abdul Rahman, you ready for the interest formulas?
Yes, teacher. I'm ready.
Okay. So simple interest. We get A of t equal to A naught plus Let me double check this. Never used this one. Make sure I write it down the same way as I wrote it before. Man, maybe I did that in week 6. Oh yeah, here we go. Yeah, that's what I did. A naught times RT. Okay. Okay, so here's the form for simple interest. Okay, so what does it say? It says that the amount of money that we have at the end is equal to the amount of money that we start with, plus the amount of money that we start with times a fixed rate times the number of years. Okay, so in particular, A naught times R is going to be like some number, which depends on our initial investment, and we just get that every year. So this is something like we start with $1,000, and then the next year we have 1,000 and plus 100, and the next year we have 1,000 plus 100 plus 100, but we don't earn extra interest on the interest that we already made. And then again, 1,000 plus 100 plus 100 plus 100. Essentially, we're earning a fixed amount each year. Does that make sense?
Yes, teacher.
That's,
I'm confused about the compound and continuous interest and the half-life rate.
sure. So compound interest, how does that work? We get A of t is equal to A naught times 1 plus R to the power t. This is annual compound interest. And then continuous is just A of t is equal to A naught, and instead of multiplying by 1 plus R to the power t, we multiply by e to the kt.
Which K? What does it mean K, teacher?
K is K can be thought of as R, basically. They're the same thing. So 6% annual. This tells us that R is equal to 0.06. 6% continuous tells us that K is equal to 0.06.
Got it.
Yeah, it's just a different, we use a different letter for it, basically. Don't ask why. Just, I guess the way that this was originally developed. In fact, the way that it was originally developed, they wrote A naught e to the delta t. But I guess they thought delta was too Greek for undergraduates, so we'll stick with K.
And for when we want to find the population growth, we use the continuous rate interest. That's right.
Sometimes. So like what it'll say is something like the following. It'll say like okay, well, how should I say this? these two, compound and continuous, these are two different ways of computing compound interest. Okay. And you can actually find a rate R corresponding to any given K such that these two equations will mean the same thing. And essentially, the way you see that is by recognizing that if you want A naught e to the kt to be equal to A naught times 1 plus r to the power t, then what you can do is cancel out the A naughts, and then you wind up with an equation which looks like e to the kt is equal to 1 plus r to the power t. And then you recognize that the left-hand side can be rewritten as e to the k to the power t. It's equal to 1 plus r to the power t, and then take the tth root of both sides. And you realize that e to the k should be equal to 1 plus r. And so if you set r is equal to e to the k minus 1, then this will tell you that A naught times 1 plus r to the t is equal to A naught times 1 plus e to the k plus minus 1 to the t, which is just equal to A naught times e to the kt to the t, which is equal to A naught times e to the kt. So what is this telling you? This is telling you that essentially you can find an annual interest rate R and a continuous interest rate K such that they mean the same exact thing. What's confusing about this is that those interest rates are not exactly the same. We don't get K is equal to R. We don't get this. So if you want to model population growth, you can really use either type of thing. So for example, if we have A naught equals, why don't we use P? So for population growth, use either. So say we have P naught is equal to 1 and P of 10, why don't we just do P of 1 is equal to 10, and they say find P of 2 if the growth is exponential. And we can really solve this problem in one of two ways. So I'll do one with just 1 plus r, and I'll do one with e to the kt, all right? Sound good?
Sounds great, teacher.
Okay. So if we want to do this one, we would use the formula a of t equals 1 p naught times 1 plus r to the power t. And what's our information? We know that 1, this should be p of t, 1 is equal to our initial population. This is p naught, and then the other thing says p of 1 is equal to 10. That tells us that 10 should be equal to 1, that's our p naught, times 1 plus r to the power, well, we plugged in 1 year for this, so 1. So we get 10 is equal to 1 times 1 plus r is equal to 1 plus r, so r is equal to 9 in this case. So we get an equation which looks like P of t is equal to 1, our initial population, times 1 plus 9 to the power t, which just looks like 10 to the power t. So therefore, if we want to know what is P of 2, we just plug in, we get
100.
Yeah, 10 to the power 2, which is just 100 people. Okay, so that's one way we can choose to view this. We can use this equation. Okay, but the point here really is that both of these equations
Are the same.
are sort of the same. And what I mean by that they're the same is I mean that they're both exponential equations. We have an a naught, an initial value, being multiplied times some number, which is being raised to the power t. So we can view this again in this other way by doing the following. If we package p of 1 equals 10 in terms of p of t equals p naught e to the kt, then we know that p naught is equal to 1. And then we would get the equation p of t is equal to 1 times e to the kt. And then we know that p of 1 is 10. And that's equal to e to the k times 1. So therefore 10 is equal to e to the k. And so k is equal to ln of 10. We're going from this step to here. I just took the ln of both sides.
Yeah.
So then if I take the equation p of t equals e to the ln of 10 times t, and I plug in p of 2, I get e to the ln of 10 times 2. And then I can move this 2 inside of the ln, and I would get equals e to the ln of 10 squared, which is 10 squared, which is 100. Does that make sense?
Yeah.
Or I could instead of doing this, I could also say that this is equal to e to the ln 10 squared, which is equal to 10 squared, which is equal to 100. That's also fine. So the point here is that you can use either equation if it's just specified that the growth is exponential. So I might have done an example where I used one or the other, but it's not to say that that is the way that you have to handle population growth or like bacteria growth or radioactive decay. Oftentimes you can use either, but the thing that you need to understand is that if you're given a rate, if they say something like 6% continuously,
You have to use the continuous interest.
you have to use
Yeah.
P of t equals P naught e to the kt and let k equal 0.06. But that's not about the math, that's about the words. And if they say 6% compounded annually or yearly or something like that, then you should use P of t equals P naught times 1 plus r to the power t with r equal 0.06. And while you can find k and r, which will make these two equations the same, if you plug the same 0.06 in for R as you do for K, you don't actually get the same thing. In fact, we saw that today or yesterday in this equation, in this problem here. We had this problem where they said, find the time required for an investment to grow from 10,000 to 18,000 at an annual interest rate of 6% compounded yearly versus continuously. And we found that the time was different for each.
Yeah, I remember that.
Okay, but sometimes what they'll do is they'll give you a problem which will say something like this. They'll say a bank offers 5% compounded annually. Find the equivalent continuous interest rate. And in this case, if we had a problem like this, we can actually solve this and we would get something like the following. We'd set up first A of t is equal to A naught times 1.05 to the power t is equal to A naught times e to the kt, and we're supposed to find out what is k. So all we do to solve this equation is cancel the A naughts, and we have 1.05 to the power t is equal to e to the kt. We take the ln of both sides. And the right-hand side just becomes kt, and the left-hand side becomes t times ln of 1.05. And then we cancel t. And we're left with k equals ln of 1.05, which if we plug into our calculator, something like 0.048790164. So in other words, 4.879% being compounded continuously is equivalent to an interest rate of 5% compounded annually. Does that make sense?
Yeah, that makes sense. I have the last question about this boring question about interest. Is the half life?
Sure. So, if we have a half-life problem, a lot of the times we tend to frame those in terms of the sort of continuous decay. The reason being that, you know, a bank may wait to compound your interest until the end of the year, right?
Yeah.
But a process like radioactive decay is happening at a constant rate, and it's not like at the end of the year the thing just magically poof, half of it's gone, right? It's like it happens slowly over time.
Yeah.
So it's a continuous process. So we use the continuous model typically. So for half-life,
I think I'm confused about just the names of the lectures.
yeah, so this is a name which just comes from chemistry, basically. or physics, however you want to view it. And it says the following: you have some mass of stuff. So, you've got your radioactive thing here. And what's happening is it's basically emitting radiation. And as you wait, what happens is you might originally have like 10 kilograms of a substance, and as the radioactive decay happens, particles keep flying off and flying off and flying off, and then sometime later we have less, maybe 5 kilograms. And the amount of time for it to decay to half its original mass, we call this the half-life. So there are various substances out there that have different half-lives, like cesium has a half-life of like 10,000 years or something like that, which is one of the reasons that it's sort of a problem when you create nuclear waste, is because it's highly radioactive and it doesn't go away for a really, really long time. So it's very dangerous, and you have to consider, where am I going to put it? Yeah. So the reason we use this continuous model to measure half-life is because this particle emission is happening all the time, and it never stops happening, so we just can use the continuous model. And so if we want to find out what the half-life of a substance is, well, we just want to know for which t is the following true. A of t, so at the end of this amount of time, how much of our substance do we want to have left? Well, we should have 1/2 of our original substance. And that we know that that is equal to A naught times E to the, I don't know, it's something like maybe minus 0.06 t or something like that. And we take this equation like this and we solve this for t. So that's kind of the general game that we play with this stuff, but maybe I can give an actual example.
Yeah, please.
So let's say 12 kilograms of a substance decays to 9 kilograms in 3 years. Find the half-life of the substance. So first of all, what should be our equation that we're working with?
The continuous interval.
Okay, and how do I write it down in this sort of general form?
AT equal to A and E to the power KT.
Great. So now how should I proceed?
Since we have A, which is equal to 12 kilograms, and the T is 3 years, No, I'm sorry. The K is 3 years, I think.
Okay, so first of all, here's what I want you to remember. K here is a rate of decay. So it'll be a percentage or something like that. T here stands for time. So if we think about 3 years, this is an amount of time. So I think you're right, we should have t equals 3. Okay, so we've got here 3 is taken care of, 3 is t, 12 here is our a naught. What's 9?
Not sure.
So 9 kilograms is the amount that we have after 3 years, right? And this equation here expresses this left-hand side is the amount left after t years. And it says it depends on the amount we start with times this thing, which is some kind of decay factor. So if we have 9 kilograms left after 3 years, we know a of 0 is 12, we know t is 3. This left-hand side is going to give us then something is equal to 9. What should go on the left side? So the left-hand side here, a of t, expresses the amount left after t years. We know that there's 9 left after 3 years, so we call this a of 3. Do you see why I put that there?
Yeah.
So now we just take this information and we plug it into our equation. So what do we get? On the left-hand side, a of 3. Now what should this be equal to?
Half. 6.
Hang on. First we have to figure out what the rate of decay is, because this is the problem. We don't know what k is. So ultimately, you're right. We want to do 6 is equal to 12 times e to the k times t, and we want to solve this equation for t. Right? However, there's a problem, big problem, which is that we won't be able to solve this problem for t if we don't know what k is. So first, we use this information, a of 3 is equal to 9. So we know that 9 is equal to our original amount, 12 times e to the k times 3. So we solve this equation for k. Okay, because this equation has only one unknown, just the k.
Yep.
Once we get the k, we'll take it and we'll plug it in to this equation, and we will have only one unknown, and that'll be the t, and we'll be able to get it. Does that make sense?
Yeah.
Okay, so let's work on solving this equation for k. How do I do it?
By using the natural log.
Something I can do before that that'll make it a lot simpler.
Dividing each part, each side with the 12.
Yeah. So we get 3/4 on one side is equal to e to the 3k. So now I can go ahead and apply the natural log, right? So what do I get? ln of 3/4. And on the right-hand side, what do I get?
And 3k.
That's right. Now how do I get k?
And k is equal to ln 3/4 over 3.
Perfect. So now what we're going to do is, like you said, solve this equation for t. Only we know that 6 is actually equal to 12 times e, and we're going to replace k by ln of 4/3 over 3. So how do we solve now?
As usual, defining by 12. We'll just have the rest e to the power for ln. T will be equal to use the natural log for each side to cancel the e.
Okay. So what do we have on the right-hand side?
Just ln 4/3 t. And t will be equal to ln 4/3 over 3 over half over ln.
So you said ln of 4/3 over 3 times 1 over ln of a half. Okay, hang on. I think something might have gotten a little switched here. If we want to undo, we might get t by itself. T is being multiplied by a fraction. How do we undo? If I have the equation 4 equals 1/2 t, how do I solve this equation for t?
T will be equal to 4/2.
4 over 2. So I divide the left-hand side by 2, and I divide the right-hand side by 2. I would get 1/4 t is equal to 4 over 2.
Oh, that doesn't make sense. I think 1 over 8. It's not make sense.
If I have t over 2, or 1/2 t, I could rewrite this equation, right? Like t divided by 2 is equal to 4. How do I undo a division? What's the opposite of division?
Sorry, t will be equal to 8.
Yeah, we should multiply both sides by 2, right? So if I have 1/2 t, I should multiply both sides by 2 over 1, the reciprocal of this number. Right? And we would get t is equal to 8. Okay, with that in mind, how do I undo this multiplication here?
T will be equal ln, so it will be t will be equal to 3 ln over ln.
Yeah, that's what we do. So what I was looking for here is that we should multiply by the reciprocal, right? 3 over ln of 4/3. And then on the same on the other side, 3 over ln of 4/3. And then this ln of 4/3 cancels, the 3 cancels, and this whole thing is just 1. So we get, like you said, t should be equal to this. Okay, so if we plug that into our calculator, let's see here. Okay, so ln, no, it was 3 ln of a half over 2, and we divided that by ln of 4 divided by 3, and we get, uh-oh, something's gone wrong. Oh no, wait, what has gone wrong? This is supposed to be 3/4. I don't know how. We copied it down wrong. See what I mean?
Yeah.
So this should be 3/4.
That's one my mistake. Sorry.
And then this will be 3/4 here. So if we plug it into the calculator, this 4/3 here in the bottom should have been 3/4.
Yes.
And that should give us a number which makes more sense, 7.22. So our answer is something like 7.22 years. Okay.
Okay. That makes sense, teacher.
Yeah, so the first step, before we get going on, I think you got a little bit ahead of yourself trying to do this first. Before we can figure out that equation, we first have to use all the information in the word problem to figure out as much as we can about our equation before we start solving. And in our case, we didn't know what k was. So we had to use this information, which we kind of took out of the word problem, and we wrote it down in this equation. We said a of 3 is equal to 9 is equal to 12 times e to the k times 3. And physically, what this equation says, if I write 9 equals 12 times e to the k times 3, what this says is if I start with 12 kilograms of a substance and I decay at a rate of k% per year, and I wait 3 years, then I have 9 kilograms left.
Sorry. Yeah. I got it, teacher.
Cool.
Thanks, teacher. I was
Yeah.
confused a little bit about the names.
Yeah.
I'm studying electrical engineering. I'm not into the names. I'm into the production. That's it.
Yeah. So then let me throw out a couple things here for you in terms of the names. Half-life is the time t such that a of t equals 1/2 a naught. That's what half-life means. Doubling time is the other one. So the amount of time it takes for an investment to double in value. That's going to be t such that a of t should be equal to 2 times our original investment. Yeah, those are really the main ones that you come across in the word problems. So usually these word problems work in the following way. We have like a word problem, and then we have an equation like a of t equals a naught e to the kt. Sometimes up here, they'll give us something like k equals some number, a naught equals some number, find t so that a of t equals some number, right? And they give us everything, in which case we just plug everything in and we wind up with an equation which looks like, you know, a number equals a number times e to a number times t, and we just solve this for t. Okay, that's sometimes how that works. The other way this sometimes works is rather than telling us that k is equal to a number, they don't tell us that. They just tell us something like a of some number equals some other number. And you have to use this information and plug it in to our equation to get something like number equals a naught e to the k times a number. Oops, so this should be a number as well. And then you solve this for k. And then you wind up with having the thing that you need to eventually do the last step.
Can you scroll up? Scroll down.
Right there? Or higher?
Oh, higher. Yes. Okay. Thanks.
Yeah, no problem. You want to talk over some more examples or a different topic?
No, I will come in tomorrow if I have anything.
Okay. All right, that sounds good then.